Thanks very much to Jeff and to the organizers for inviting me to this fantastic place. It's a very nice conference, so thanks a lot for having us here. I will talk about some work, and part of it is with Adam Koborinsky, who's here as well, and who is a PhD student in philosophy at a beautiful Western university. So here's a quick outline of the talk. The part with Adam, where we work together most, is the third one. In the third part, I will argue that you can see quantum theory as a principal theory, in some sense. Now, I'm sure lots of you will disagree, and I'm happy for discussions about that. I would just encourage you to do that after the talk in the discussion part, to talk about this. Now, in order to get there, I will talk about the reconstruction of quantum theory from information theoretic principles, which will be the second part. And in order to get to the second part, I have to tell you from what landscape of theories we actually reconstruct quantum theory. So the first part, which I will start today, will be to show you how physics could actually be different from quantum theory, for those of you who haven't seen it yet, and how to understand this landscape of probabilistic theories. And then, since I'm a physicist, I wouldn't give too much weight on these interpretational issues, so I hope to find some time in the last part of the talk to talk about some other consequences that one might draw from these reconstructions. For example, about experiments to test quantum theory, or something we can learn about the relation between information quantum theory and space-time, hopefully. Okay, so in the first part, what is a probabilistic theory? How can physics be more general than quantum? So the starting point is to take a very pragmatic view on the quantum state. The starting point is to say, what is a quantum state? Well, it is the thing that allows us to determine, for all possible questions that we may decide to ask a physical system, the probabilities of finding the possible answers. So it's the thing where we can compute probabilities from. And I would argue that this is the part of quantum theory where all interpretations basically agree. That's what we do when we go to the lab and test it. And once we have a quantum state, we can ask then, well, what is it? Okay, now first an example. This is an example of a question we might ask to a physical system. The system could be the silver atom and one of its degrees of freedom. And we might ask, do we find the spin up in z direction in this arrangement, yes or no? And then the probability of yes will be given by the Born rule. In general, it's just an overlap between the quantum state and the projector. So the quantum state is the thing that we put in here to get the right probability out. Now then, if we have that, then what is a Hilbert space? What is, say, a space of density matrices? Well, it's just a collection of all the states that a system could possibly be in. And it has the important property that it's closed under taking probabilistic mixtures. So you can always think of doing the following. You can say, well, let's toss a coin or some die. If you get an even number of coins, you prepare psi. If an odd number, you prepare phi. And then you get a mixture of psi and phi, which is just a density matrix. So that's for quantum states. Now what about more general state spaces? So instead of a quantum state, you would just talk about a state in general. But the interpretation is exactly the same. We say whatever the state is, it is just the thing that allows us to determine all the probabilities of the possible answers to possible questions we might ask for a physical system. Now what is a state space in general? Well, we don't have a Hilbert space anymore, density matrices, but we still have a state space, which will be something that's closed under taking mixtures like this. I can still throw a die and prepare one of two states with probability 50-50, for example, and make sense of this expression here, and say this is just another valid state. So it turns out that there's a vast landscape of possible theories where this prescription fits in. I can talk about state spaces or theories, which are collections of state spaces. And so, for example, there's quantum theory where state spaces are given by sets of density matrices. CPT here will be classical probability theory where the states are probability distributions, but they're more interesting in more general things. For example, it's something that Jeff would call banana world and people in quantum information theory would call box world. I'll talk a bit about this. The C-star algebras and state spaces are in there and so on. Now the goal is, give a set of principles that from this landscape singles out quantum theory uniquely. But to see how that goes, we first have to see a bit more details of this formalism. How do we describe these theories in there? And to be clear, this will be formulated in some instrumentalist way. I will motivate the mathematical formalism by preparations, transformations, and measurements, but it's not the only way you can actually interpret this formalism. So then how do you describe one of these theories? Well, essentially, what you find is that state spaces are these kinds of things. So these are just convex sets that are closed, compact, but they can be really arbitrary convex sets in some vector space over the real numbers. And why is that? So here's a possible motivation. Think of a typical laboratory situation that you might want to describe. You have something like a preparation, transformation, and a measurement. And in the simplest case, for example, you can have a classical coin toss. So the preparation device just tosses a coin, could be a fair coin or not a fair coin, and then you get something out. Then you can transform it, and maybe the transformation device just rotates the coin, puts heads to tails and tails to heads. And in the end you find you do a measurement. The measurement could just be, look if it's heads, and if it's heads, then flash a green light. Now mathematically you would say, well, what's the state that comes out of the preparation device? It's just a probability distribution that we can find if we repeat this many, many times. You would have a probability of heads and a probability of tails, and you would call it the state omega. And what's the state space? Well, it's all the possible states of this form you can have, so it looks like that. You could have a coin that's always heads, or a coin that's always tails, which would be the pure states of the theory, or some probabilistic mixture like a fair coin here in the middle. What a transformation would do is it would map a state that's ingoing here to an outgoing state, and if it just flips the two outcomes, then this would be a linear map that just, does this transformation here. And it maps states to states, it's a linear thing, a linear map. And then the measurement outcome probabilities, what would that be? Well, probability for finding heads would just be p here, but then p, you can express it as a functional on the state. You take the state and you read out p, that's a linear operation. So you have a linear functional on the state that gives you outcome probability. Now you already see a pattern here that actually fits the quantum theory as well. If you think of a spin 1/2 particle, the preparation device would now output a quantum state, a two-level quantum state. For example, a superposition of spin up and down, but it could be a mixed state. So in general we have a density matrix. And here's a way to parameterize density matrices that I guess most of you will know. So you can just introduce theta and phi, two angles that parameterize this quantum state, which will give you a ball, a sphere actually. And then the mixed states will just be in the interior of the sphere. So the state space, in this case, is a three-dimensional ball, the Bloch ball. And what transformations do, they could be unitaries, for example, and what a unitary does to the Bloch ball is it rotates the Bloch ball, that's one state to another state. Now the measurement probability, probability of finding an outcome would be again something that's linear in the state, and all you do is you take a projection operator and take the trace according to the usual rules. So in general, when you abstract from this, you would say, well, what I have always is just a set of possible states, omega, state space, and it has, we can choose it as we like. There are no restrictions so far, but we want one thing to always be possible, namely to prepare mixtures. We can think of devices like this that randomly prepare one of two states. What this tells you is that the state space should be closed undertaking convex mixtures like this. So this state space should then be a convex set. But that's basically all we really assume. In quantum theory, this convex set would be the density matrices. In classical probability theory, over n outcomes, this would just be the probability vectors with n non-negative entries that sum to 1. Good. Now, you can have all kinds of state spaces. So here we've seen a couple already. This is the classical coin, the classical bit that I've shown you. The quantum bit is something like a 3-ball. What would be a classical 3-level system? Well, you have 3 possible outcomes and their mixtures. So you can always get a simplex classically, in this case a triangle. The quantum trit looks quite funny. So this is by a paper by Bengtson, who tried to depict what the 3x3 density matrices look like if you do it as a convex set. It's quite complicated. It's an 8-dimensional convex set that has some flat parts on the boundary, but lots of symmetries and so on. Well, that's what it looks like. But you can have anything in this framework, like really any arbitrary convex set. And for example, quantum information theorists have studied this thing, the square state space, for some reason that may become interesting and clear a bit later. So all they fit into this landscape somehow. So here's its quantum theory with its kind of state spaces that it allows, classical probability theory with its state spaces, all convex sets appear somewhere, and here's banana world. Good. Now, the first thing to ask before we go to the construction is, what would actually happen if one of these other theories applied to physics? How would physics be different? Would our world look somewhat differently? And one thing that you can have, which would be different, is you can have beyond quantum Bell inequality violations. Some people just call it post-quantum non-locality, something like this. So in this case, you just go to a Bell setup, a Bell scenario. You have Alice and you have Bob. Alice has a choice of maybe they share an entangled quantum state or whatever it is. And now Alice has a choice of measurement. She can, for example, choose to measure spin in Z direction or spin in X direction. The measurements are labeled 0 and 1. And she will find one of two outcomes in this case, say plus or minus 1. Same for Bob. Now, in quantum physics, we know that these probabilities of the outcomes given the settings are simply calculated by the usual trace rule of projection operators in some quantum state. Classical physics, if you assume that there's shared randomness, lambda, that has been distributed to A and B beforehand, but they cannot communicate otherwise, you find an expression like that. And now, as all of you know, well, that's something else I want to say first, namely, here's something important about both cases, the no signaling principle. So basically, so if you just look at Alice's laboratory, then whatever she sees here is independent of Bob's choice of measurement over there. So if you write it down, what that means is you can just sum over the outcomes of Bob, get the marginal, and this will not depend on B. And that's important because if that was not the case, and they lived very far away, then they could build a Bell telephone and signal instantaneously. But this condition rules that out. So that's a no signaling principle. That's true classically and quantumly. Now, as all of you know, classical probability distributions of that kind satisfy Bell inequalities. For example, the CH-SH inequality, where you compute these correlators here, you get a value less than 2 classically, whereas quantumly, you can get more. You can get 2 square root of 2. And so here are the possible values. And what Popescu and Rohrlich asked a couple of years ago was, is that the most general thing you can imagine if we only assume no signaling? And the answer turns out, perhaps surprisingly, no, it's not the most general thing. There are correlations, so-called PR box correlations, for example, that are even stronger and violate this bound by even more. And here's one of them. So, in order to give you the correlation, I have to write down what these probabilities are. And here's a probability table. So, the blue ones are the choices of measurements. So, if Alice and Bob both choose measurement number 1, then they get anti-correlated outcomes with certainty. But it's kind of random which of the 2 cases they get. But in all other 3 cases of choices of measurements, they get perfectly correlated outcomes. Now you can check that this satisfies the no signaling principle, but you get a value of that expression of 4. So this is more than you could get within quantum theory. So if you draw a picture of these correlations, of these probability tables, you will find this kind of polytope of the P of xy given ABs, where I say, here are all the non-signaling correlations, then there's a subset what I can realize in quantum theory, and an even smaller set that I can realize within classical physics. And you can ask, why does physics seem to disallow this red area but allow the blue area, for example? And you can ask all kinds of interesting questions. But here, the only thing to see is that this polytope itself is actually a state space inside this landscape, namely banana world or box world. That's a composite state space, as it turns out, of 2 of these square state spaces. So physics could be different within this landscape in the sense that it would be more non-local in the sense I described than quantum theory. But there are other possibilities, and I want to show you one more. And that's called higher order interference, which is also actually tested experimentally. Now, what's higher order interference? Or what's third order interference? Well, it goes back to Sorkin in '94, and here's the main idea. So this is a double slit experiment that all of you are very familiar with. You have slit number 1 and slit number 2. You have a particle that impinges on the slits, and you have a detector here that can click or not click. What about the probability of the click? I can play a game and say, well, let's first determine the probability of the click if I block slit number 2 and only slit number 1 is open. and call this, as slit number 1 is open, call this probability P1. Do it the other way around and call it P2, or then leave both slits open and call that just P1, 2, because slits 1 and 2 are open. And now, in classical probability theory, if you have a soccer ball and you kick a ball, you would expect that the probabilities just add up. But we know that in quantum theory they do not add up, and that's what we usually call interference. So far, so simple, but the surprising thing is what happens if you add a third slit. So what you can do is you can play the same game. You can have all 3 slits open, you can have 1 of the slits open, you can have 2 of the slits open, and then see what probabilities you get. And perhaps surprisingly, both classical physics and quantum physics satisfy this equality. Namely, the probability you get if all 3 slits are open, P1, 2, 3, can be decomposed into pairwise and single slit contributions. And in this sense, we have no third order interference in quantum theory or classical probability theory. So violation of this inequality is what Sorkin would call third order interference. And now you can go into the laboratory and build some slits here, move them around, have photons, count them, and then try to actually experimentally determine whether the difference of this equation of both sides is 0 or whether it's non-zero. And then you find it's really small. So I think back then they found it's less than 10 to the minus 2, but now I think they're down to 10 to the minus 4. Okay. So this was just an example. We can see physics there would be other possibilities a priori how physics could behave in the laboratory. And they are all summarized in this landscape of probabilistic theories. Now in the second part, I will show you a reconstruction of quantum theory that picks out quantum theory from these possibilities. So we're again here. And what I will do now is I will describe one particular set of principles that really does this. It's in this paper here with Luis Massanes, Vinicius Abuziak, and David Perez-Garcia. But I would emphasize that this is not the only one, and many others have been found in the last few years. So here's a very short history slide. Obviously, people have tried something like that for a long time. In quantum logic, they tried similar things. But I think that the revolution really started with quantum information theory, what Lucien Hardy did in 2001. Lucien Hardy found a reconstruction of quantum theory. But the only problem with his reconstruction is that he has one axiom that he calls simplicity axiom, where he basically says, oh, among all the infinitely many possibilities, choose the simplest one. And that's not really a good axiom, because it's not very precise. So people have tried to make it more precise. But first there was this paper by Otto Cheff and Clifton and Halverson, where quantum theory was derived from axioms in a really nice way. But also this has a problem, namely, as Cheff also said now, that the assumption already here was that you have a C-star algebra. But if you go to this landscape, the C-star algebra, a little island here, that already is super close to quantum theory, or actually are quantum theory in some sense. So then you might want to do more. And in the general probabilistic framework, it started in 2009 with Časlav was here too, and with Vojvodina Dakic. And then things took off, and many other results appeared. Alex contributed to it, who's here today, and Howard. And I will talk about one from 2013, actually, today, one of those. So which principles could give you quantum theory here? Now here we have one which needs 4 principles, and let me just name them one by one. First, okay, so here's a paper again, but the first principle is continuous reversibility. And it says basically, so I will not give you the mathematical formulation, but just the meaning. And what it says is that continuous reversible time evolution can in principle map every pure state of a system to every other pure state of a system. So if you think of a spin 1/2 particle of a Bloch ball and the pure state, then you can rotate the Bloch ball to get the pure state to any other pure state, and you can do that continuously. You can think of that as continuous time evolution, moving your pure state over to another pure state. That's continuous reversibility, and it's true for quantum theory, and here it's elevated to a postulate. Second postulate is tomographic locality, and it says that the state of a composite system is completely characterized by the correlations of measurements on the individual components. So here's a way to understand this. You have Alice and you have Bob, and somebody gives them an entangled quantum state. Maybe many copies of that state. And their task is to find a description of that state, like what density matrix represents that. And now what they can do is just do local measurements. Alice does local measurements and Bob far away does local measurements in his lab. And then they talk on the telephone and compare the outcomes. And that's sufficient to reconstruct the state. So they do not have to do global measurements to find the state. Third one, existence of an information unit. So what is this? Basically says that there's something like a bit. It says that there is a type of system, the U bit or universal bit, such that the state of any system can be encoded into a sufficiently large number of these universal bits. So think of here your favorite physical system, an atom or something, maybe finite dimensional, we restrict ourselves to finite dimensions here. It's in some state omega, and here you have a number of bits in an initial state. Then you can have this encoding process, which basically moves the state omega to the bit systems, and then possibly also erases or changes the state of your physical system.
Sufficiently large always is finite, however, yeah?
Pardon?
Sufficiently large number is always finite.
Finite number, yes. Finite but sufficiently large. Also, I'm restricting myself here to finite dimensional state spaces all the time, I should say that. The crucial thing is you can go backwards and you can decode again in a lossless manner, if you like. And what you also want, and that's kind of contained in postulate 1, depending how you read it, is that if you have more than one bit, you have two of these bits, then they can somehow talk to each other. They can interact continuously and irreversibly in time. I will say more about this part in a second. So, but this is true classically. Classically, just classical bits do the job. In quantum theory it's true because we can encode a state on a number of qubits. And here it is a general postulate. Last one goes back to Zeilinger, and it's called no simultaneous encoding. Basically it says a bit is a bit and not a trit, something like this. So it says if a universal bit is used to perfectly encode one classical bit, then it cannot simultaneously encode any further information. Quantum theory means that if you have a qubit and you encode, say, 0 or 1 as a classical bit, then there's no more things you can do. You kind of exhaust the state space, and that's all you can do. And here it is a postulate. And now you can prove a theorem. You can say if these four postulates hold, then the state space of these n qubits is exactly the state space of complex n-qubit quantum theory. So the states are the n-qubit density matrices, the transformations are the unitaries of n-qubits, the measurements are given by the trace rule and the positive operator value measures. And the kind of cute thing is that you can draw a picture for the proof, and that's a picture how the proof works. So we start with a single universal bit. It has some state space, we don't know which one, we don't know its shape, it's some convex set, and we don't know its dimension, we know basically nothing. Then we look at the postulates and say, oh, no simultaneous encoding. What does that mean? Well, if you look at it carefully, you see that means actually that the state space cannot have any flat pieces in the boundary, because the flat piece somehow could be used to encode extra information. Now that's not obvious what I'm saying, but let me just give you an idea. So this means that your state space must look round somehow, like a droplet or something like this. Now continuous reversibility tells you can move one state to another continuously, and this maps states to states. This makes your state space very symmetric. And group theory tells you that the state space actually must be an ellipsoid in order to satisfy this. But if you're an ellipsoid, you can just redefine the coordinates to get a ball, and here's your Bloch ball. But what we don't know there is the dimension of this Bloch ball. In quantum theory it's three-dimensional for Pauli X, Pauli Y, Pauli Z, but it could be anything a priori. And then we have to do some, invoke the other postulates, and actually we get it must be three-dimensional to satisfy these postulates, which is the hardest part here. Once we have that one universal bit is described by a three-dimensional ball, it takes still more work to say that if you have a bunch of them, that the only way to do this consistently is in fact in the quantum way. So let me talk about this part a bit more. Shouldn't be brown. Anyway. That's a paper on its own, and what you do here is you look at two of these universal bits. So here's a universal bit A, a universal bit B. Both are described by a Bloch ball of dimension D. And I ask, what can happen with these two? In particular, you look at the joint state space and ask what time evolution could I have on that. And it turns out if the dimension is not 3, then all continuous reversible transformations that you could have must be of the form transformation on A, tensor transformation on B. So they evolve independently, don't talk to each other. And that's the only possibility no matter how you actually choose your composite state space. And no matter what the dimension is, as long as it's not 3. Yeah, and you can cook up a group theoretic reason, you look at a long proof, and it all boils down to the group theoretic fact that rotations commute in 2 dimensions and not in higher dimensions. Which is not so important, but then this is really a theorem. So let me just say this is really surprised us that you can really make such a statement, because I think it's pretty strong. So you have these local state spaces which are balls, and you assume you have any composite state space, whatever that is. There are infinitely many possibilities to do that. You only want that you can have product states in there, or product measurements, and you can do your local transformations. And then you only either have the trivial solutions for the transformations on AB, or you have the solution that the dimension is 3, you have the 3 ball, you have the rotations of the 3 ball, and the transformations on AB is the unitary group, the projective unitary group on 4 outcomes. So in some sense, continuous reversible interaction is a very strong assumption that gives you exactly the quantum state space here. Now, I think you can already learn something from that. Chris Fuchs in 2002 has written a paper where he kind of brought up a challenge, where he said, let's derive quantum theory from information theoretic axioms. And with this table, why are measurements and transformations completely positive linear maps? Give an information theoretic reason if possible. Give an information theoretic reason for everything. Then he says, but then if we have the distant that remains, the piece of quantum theory with no information theoretic significance, will be our first unadorned glimpse of quantum reality. Somebody says that the part that's not information theoretic, that tells me what the world really is like in some sense. So do we have that here? It's not so clear. So first of all these 4 postulates that we have here are in some sense or another information theoretic, I would say. But I would argue that the first one is a little bit less so. In particular, that you have continuous reversibility. That's somehow characteristic. Why not just reversibility? And I think that's maybe a distillate that remains here. Now to clarify this even a bit more, P2, P3 and P4 are actually all true classically, for classical probability theory. And P1 is the big difference. Namely, if you think of classical systems, then continuous reversible time evolution is classically impossible for finite dimensional discrete systems. Now, here's a finite dimensional discrete system. You have a ball that's either left or right. Only these 2 possibilities. Your state would be a probability assignment. You would have 2 pure states. Here you know perfectly the ball is left. Here you know for sure the ball is right. But in order to map one to the other, you can only swap the balls, which is a discrete transformation. There's no continuous way to do it. All you can do continuously, classically, is to add noise. You can make that 0 to 0.1 and so on, make it more noisy. But that's not reversible. You cannot go back. But quantum theory allows you to do that. Quantum theory, if you have an eigenstate of left, you can evolve it continuously in time with a suitable Hamiltonian, and at some time t0 you will actually end up with right, if you do it in the correct way. And you can see that on the shape of the state space. Classical state spaces are discrete objects, you can only permute them. Quantum state spaces have these continuous symmetries that allow you to do these transformations. And usually what you learn when you study quantum physics is, you can have classical systems that are continuous, and quantum theory discretizes them. This is, I think, a kind of remarkable inversion of that. Tells you something that's discrete classically can be continuous quantumly, and that's a characteristic feature. Good. Now the third part. I'm really looking forward for discussions later after the talk.
Marcus?
Yes?
It's just a quick one.
Sure.
Was there any assumption at all about the physically allowed measurements sort of being the full set of mathematically possible maps on the state space? Yes, there is.
So I'm dropping some details. So the thing is, in this framework you can make an assumption or not make the assumption, and that's if you have a state space. Does that determine the set of measurements? Yes or no? And the answer is yes, it does here. So all measurements that give probability spin 0 and 1 are assumed to be possible in principle. I didn't mention it because I wanted to keep it simple, but yes. So what can we learn from this? And this is in a paper that Adam and I have written up. And what we do is we argue for the following. Here's a thesis. We say, well, information theoretical reconstructions provide a partial interpretation of quantum mechanics as a principal theory of information. This leaves several alternatives for extending to a full-fledged interpretation. And these reconstructions, we think, also present a major challenge for existing psi-ontic interpretations by highlighting a relative deficiency of these interpretations in terms of the explanatory power. Now, I will go through that. Let me just say that this is not new. All of that has been said one way or the other. In particular, Jeff has said a lot of this in more detail in his book. But Laura Fellini has also said more about how to understand this as explanatory power than explanation in a paper in much more detail and more beautiful than we do here. So this is not really new, but let's go through it and maybe see whether the reconstruction can serve as an illustration of this and see what we get. So the first part is we think that reconstructions are a partial interpretation as a principal theory of information. Why is that? Well, the idea of a principal theory goes back to Einstein, as most of you know, and here's one possible citation. I will not read all of it, but what he says here is like we can distinguish various kinds of theories in physics. Most of them are constructive. They attempt to build up a picture of the more complex phenomena out of the material of a relatively simple formal scheme from which they start out. Like the kinetic theory of gases seeks to reduce the movements of molecules to build them up out of the hypothesis of molecular motion. So that's what he calls a constructive theory. But then there are also principal theories, and the elements which form their basis and starting point are not hypothetically constructed but empirically discovered ones, general characteristics of natural processes, principles that give rise to mathematically formulated criteria which the separate processes or theoretical representations of them have to satisfy. Yeah. Like thermodynamics, where you have thermodynamic principles that allow you to draw conclusions from the principle. Now, I would say you can view these four postulates as one instance of that. So, you'd say these four things here identify a small set of information theoretic principles, or if you want, computational principles, which render our world a quantum one. You think this can be called a principal theory. In what sense is it a partial interpretation? Well, what we find here is that the quantum theory formalism is found to be the unique consequence of easily understandable constraints. So the complex numbers, the operators, and all these formal parts of it do not have to be postulated a priori, but they appear automatically as consequences of the postulates. And I would also say that this framework is very suggestive of the interpretation that a quantum state, the quantum states are just the same kind of stuff as probability distributions are in some sense or another. And here's one very nice illustration to see that. Replace postulate 1. So postulate 1 was continuous reversibility, replace it by discrete reversibility. And what you find is that the only solution now is just classical probability theory. So, but then maybe this tells you that these two theories are actually somehow very closely related. Then this leaves several alternatives for extending to a full-fledged interpretation. Well, so these reconstructions phrase quantum theory as a principal theory, not a constructive theory. For example, they typically do not tell us what quantum states really are, or what is really going on in the world, for example, during a Bell experiment. So you might want to answer these questions, or maybe actually you would not want to answer this question. But anyway, you can use it as a starting point and say, let's try to find a full interpretation, and here are three options. And the third option will actually dismiss this objection right away. But here's option 1. Just adopt a subjective view of the quantum state, or something that Cabello and other people call the participatory realist interpretation of quantum theory. So these are variants of the Copenhagen interpretation, cubism, Bruckner and Seilinger's view, Wheeler's interpretation. We say quantum states are not really things in the world in a very strong sense, but somehow express our knowledge or information or belief about the world or about things in the world, or future experiences which are caused by things in the world. So that's one way to have an interpretation from the information that is reconstructions. Option 2, actually come up with a constructive successor of quantum theory. So find something that describes a regime of our world that is currently empirically inaccessible, but which gives rise to the information-related principles, and so indirectly to quantum theory after some approximation or post-graining. And the historical example of that would be the kinetic theory of gases, starting as a constructive successor of thermodynamics. And now this historical example makes us optimistic because it says, well, here, actually the development of this better constructive theory was guided and constrained by these principles, by the presence of the principle theory. So if you want that kind of thing, you might say, well, it's probably good to have these principles because they can guide the development of the constructive theory. Option 3, this is a very rough sketch. I'm not saying too much here, right? It's just to lay out a very broad possibility. Combine quantum information theory with ontic structural realism or something like that. So what you would do here is you would just reject the ultimate need for an entity-based constructive account of fundamental physics, and you would adopt an ontology of structural relations in some way. And these structural relations are maybe expressed by the information theoretic postulates. Now, first of all, this is not very detailed, so Lucas Dunlap, for example, is working this out in more detail now. I'm looking forward to what he does there. Now, I personally find this third option like the most interesting one, because somehow it says that maybe quantum theory is not so much a problem, in the sense that we should find a successor or improve on our understanding of it, but maybe it's just in itself an exciting lesson that we've learned from nature. And we can still make sense of it without resorting to some kind of mysterious wave function ontology, like in a many-world sense, just by seeing it as it is and how it manifests itself in its information theoretic structures. Good. Major challenge for existing psi-ontic interpretations. Good. So what is this? Well, psi-ontic interpretations, most of you will know that would classify with a class of interpretations where the quantum state is viewed as an intrinsic property of the physical system in a particularly strong sense. So think of something like some stuff out there, like the electromagnetic field. And I would argue that you could somehow classify more or less those theories along this kind, quantum mechanics, many worlds, and so on. Now what's the challenge here? Let's just pick out many worlds at random and argue in this example. The challenge here is, for the Everettians, please go ahead and set up a framework of theories of many worlds, a broad framework, which is broad enough to encompass some phenomena that are impossible within quantum physics. And then give a set of simple physical principles and prove that this picks out quantum theory among the landscape of all possibilities or theories of many worlds. So that would be a nice challenge to be met, but as long as this challenge is not met, we think that there is some kind of relative deficiency of this interpretation, say the many worlds one, in terms of its explanatory power. If you compare it to a completion of the partial interpretation that you get from the reconstructions. So basically here's something reconstructions can do that it cannot do in these psi-ontic interpretations, at least as far as I know. And now Chris Fuchs has put this in a more fun way than I do, so I'm just citing him now. And he says that the idea of quantum states information has a simple unifying power that goes some way toward explaining why the theory has the very mathematical structure it does. By contrast, who could take the many worlds idea and derive any of the structure of quantum theory out of it? This would be a bit like trying to regrow a lizard from the tip of its chopped off tail. The Everettian conception never purported to be more than a reaction to the formalism in the first place. That's a more fun way to say it. Yeah. Good. Now since, how much time do I have?
About 10 minutes.
10 minutes, good. Now, so let me actually try to, I think I can do the last part now, which is less about interpretations and more about what about physics can we possibly learn from these reconstructions. And the first thing I guess that we can get a hand on is informed experimental tests of quantum theory and reasonable alternatives to quantum theory. So here's an experiment that I've shown you. It's a test for higher order interference. And the one I've shown you really was just to go to the lab and test whether this third order interference term is zero or whether it's non-zero. Now doing this is always a problem, and what you would have as an experimentalist instead is just some alternative theory that actually predicts a non-zero value. Some alternate says it's 10 to the minus 5. That's an alternative theory. Then you can go to the lab and try to falsify that theory. And one possible strategy that you could adopt here is you start with the postulates of the quantum theory, and then you drop one of them or relax one of them, and you just work out the resulting set of probabilistic theories. And then maybe this gives you a nice model for this kind of thing. Now, if you do that, you can hope for a couple of things, I guess. One thing is you can possibly do more informed experimental tests. Maybe this actually describes new physics, who knows? In the past, we often had it that we generalized our theories in some simple way and found ways in which nature really acts. But if you think that's not the case, it's still mathematically interesting to write down these theories, and for quantum information theorists it's interesting, for example, to talk about the computation in those theories and to compare their computational power to quantum computation. Now here's one way to do it, maybe, which is just, here's another reconstruction of quantum theory with Howard and Cosmin, where we say if these four things are satisfied, then your state space is a quantum state space. I don't go through these four things now one by one, but they pick out quantum theory. And what you can do is maybe play a game and just get rid of postulates. So let's drop the fourth one, energy observability, let's get rid of it. What you find is you find classical probability theory and something called the Euclidean Jordan algebras. For example, quantum theory over the quaternions appears now as a possible solution. But now the interesting thing will be to drop postulate 3. Postulate 3 is that the theory has no third order interference. So let's drop this. Another question is maybe you find new solutions here, which are not of that form. And what about those? Well, I would argue that these are the ones that do actually have third order interference, but are somehow otherwise close to quantum theory. So if these theories exist, if we find them, they are concrete models for higher order interference that allow you to go to the lab and in principle test them, hopefully. Problem, we don't know if they exist. It turns out to be mathematically very hard to decide. So even though we don't know they exist, you can do some mathematical science fiction, and you can say, you can be rigorous and speculative at the same time, and say, suppose they really exist, and let's look at their properties, let's try to prove properties they might have. And here's an example in some work with Jonathan Oppenheim and Oscar Darleston. We look at the page curve for black hole entanglement entropy. So here's like time when a black hole radiates, and here's entanglement entropy. And then this one here is the usual page curve in quantum theory, where entanglement grows, and then entanglement entropy goes down again when you have radiated away enough degrees of freedom. Now, if your order of interference is not 2, but it's 1, then you have classical probability theory, you get a flat curve, there's no entanglement at all. But if it's 3, for example, you get a curve like that looks quantum for a long time, but then in the end will depart from it. So you get theories that have physics which looks like quantum theory for a long time, but then depart from it at some point. Okay, last thing I want to talk about today is something that you can hope to learn also from this perspective, is some insights, at least little insights, into something about space-time and the structure of quantum theory. So here's a new perspective. Once you've seen these landscapes of theories, perspective is that the structure of quantum theory state space is somehow exceptionally suited to carry the Minkowski space-time symmetries. So what do I mean by that? Well, here's one thing we've already seen. We've already seen that continuous reversible time evolution is a characteristic feature of quantum theory. And as we understand it, space-time, usually we have time going up continuously and we have a state that's evolving continuously. So somehow this fits very well postulate 1 here. We've discussed that earlier on a little bit. But the same also applies to spatial symmetries. If you think of a Stern-Gerlach device, and a quantum 2-level system, spin 1/2 particle, then this is the state space of the quantum particle. It's a qubit, a 3-ball. And so the physical spatial rotations of your device, by group representation theory, just correspond to rotations of this Bloch ball. And that's very nice. If you just had an arbitrary theory like this, that wouldn't work. Try to rotate this thing and then you will map states to non-states. This cannot happen. So something is going on here. And here's another thing. So relativity of simultaneity actually, and I will just very briefly tell you this without details. says something about the dimension of your Bloch ball as well. So you think of a Mach 10 interferometer. So it's the last example for today. But think of an interferometer with an upper and a lower arm, and a particle that can be in one of these two possibilities. You can describe this by a d-dimensional Bloch sphere, like a qubit, when you say, well, if you have the North Pole state, that would mean you have a particle that's definitely in the upper branch. If in your state space you have a South Pole state, it's definitely the lower branch. If you have a state on the equator here, then it's somehow 50-50 delocalized. So if you do a measurement, you find it with 50% probability here. According to the rules of this landscape of theories, the probability of finding the particle in the upper arm would be linearly related to the z coordinate here, like 1/2 z plus 1. That's true for the qubit, for example, where this is a 3-dimensional ball. You can think of also putting little pieces of glass inside the arm. So here's Alice, she does something locally on her arm. Here's Bob, he does something locally on his arm. And now the interesting thing is the following. Let's make a few assumptions on the setup. Suppose that A and B, so these two arms are isomorphic. So whatever Alice can do up here, there's a correspondence with something that Bob can do down there. And assume also that this beam splitter in the beginning can generate any probability of finding the particle up here. Maybe 1, maybe 1/2 or 1/3, as you like, if you tune the beam splitter. And then these local transformations in your arms can actually prepare any state in your state space. And crucially, let's assume that what you do in these two arms satisfies relativity of simultaneity. That's what you really need here. These things here, A and B, are spatially separated, so there's no way to say which one happens first. There's just no order in these operations. If you make this assumption, you find that the Bloch ball dimension, that was a priori unconstrained, must be either 2 or 3 or 5. And these are the only possibilities. 3 would just be the standard Bloch ball of quantum theory. 2 would be the quantum theory where you're restricted to the real numbers. 5 would be the one where you actually have the quaternions in your density matrix. But that's all you can have. And I think this is interesting. So it's somehow, we have this strange situation that we have the qubit and quantum state spaces more generally. We get that stuff from information theoretic postulates, but its structure is also related to space-time structure, as we've seen. Now I would argue this has something to tell us, even though it's not clear what exactly, but it suggests that there will be some link, some information theoretic link between all these things. Between quantum theory, space-time structure, and information theory, in one way or the other. And maybe some of what was done here is a possible way of studying it. Other ways to study it maybe go with strategies that Raphael Busso talked about. Good. Now, just to make a little bridge to the next talk by Matty Hoban, here's a speculation. If you ask where is place for beyond quantum physics in our world, for example, almost quantum correlations, and Matty will be talking about. But if you really take the speculation seriously, which is just speculation, but suppose we do that, then maybe this means that actually these more than quantum probabilities, beyond quantum probabilities, can just be found in regimes where the standard picture of smooth spacetime and continuous time evolution is not applicable anymore. If these two things fit together so well, and you think that one of them may be modified in some regime, it's not unreasonable to at least speculate that the other one might be modified as well. Okay, so here's the conclusions. Just copied the outlook here. So show you a reconstruction of quantum theory. Then I've argued, and this is work with Alan, that you can see quantum theory as a principal theory in some sense, at least in a partial sense, as a partial interpretation. And then I've given you this outlook, what doing experiments maybe for testing quantum theory and the relation between information quantum theory and space-time. So here's some references, and yeah, I'll stop here. Thanks for